healthcare and use causality to make a better AI system. Funded by ETSRC, our mission is to conduct groundbreaking research, drive innovation, and build a community for co-creation. This is our monthly seminar, where we invite speakers for exchanging knowledge and inspiring discussion about recent developments in AI and healthcare technology research. And today we are hearing from Dr. Manling Li, who is an assistant professor of computer science at Northwestern University. Dr. Li was a postdoc at Stanford University and obtained a PhD degree in computer science at the University of Illinois, Urbana-Champaign in 2023. She works in the intersection of language, vision, and robotics. Her work won the ACL 2025 inaugural dissertation award honorable mention, ACL 2024 outstanding paper award, ACL 2020 best demo paper award, and ACL 2021 best demo paper award, and so on. She was received from the Microsoft Research PhD Fellowship in 2021, EECS Rising Star in 2022, and she served as an organizing committee and delivered tutorials at multiple top conferences. And you can find more details through her website. And today she will talk about the recent research on agents and the spatial reasoning from her lab, titled with See, Think, Act, training agents by reinforcing reasoning. So without further ado, now it's my pleasure to give Dr. Li the floor. Manling, welcome.
Yeah, I really appreciate the opportunity, and I'm very excited to share some thoughts about how to make the reasoning more kind of reliable for these large foundation models. So we actually wanted to start from some example about this generalist agent. So when I try to make the agent more clear, we actually ask a lot of people, and I think this definition is very simple, but actually defines the most important part of the agent, that they try to do many tasks in many environments. So many tasks means we want the model to do decision making to achieve the goal. And many environment means that we want the agent to interact with the environment, so they need to get the word knowledge about it. So essentially, what we try to do is like we try to transform from large language model to large agent model, so we can interact with the environment, and then we can do goal-driven decision making. So this is an example that we basically feel very surprising, like the current foundation model still cannot handle. So we just ask the model to set up the table, and the model will always put the turkey directly on top of the table. So this is something I think I tried with the most latest model, they will still do so. But as human, we actually will never do this. We will use the plates, and we will try to put the turkey on top of the plates, and then put the plates on top of the table. So I think this basically means that although the foundation model has been trained to do the reasoning, but a lot of cases, they may not ground the reasoning to very detailed, fine-grained objects and the relationship in the environment. So what we try to do is we try to learn the trajectory of how the model can achieve the goal step by step. So this is what we try to do about decision making. And then when we talk about decision making, we're trying to ground it to the macro decision process. So essentially for agent, we will have the goal as the input. And then we have two counterparts. One is the agent, another one is the physical world. So if we can have the agent, then the agent input will be the state and the reward. And then it will generate the action. The action will be executed in the physical world, and then we can get the reward and the state as the feedback. So essentially, the Markov decision process is a very fundamental framework for the research in the agent-based learning. There are several abilities we want to learn for this agent. Firstly, if we use the large language model as agent, we want them to understand the state, so that is the state estimation. Given the state estimation, what we try to do is we want to train the large language model to see the environment, especially this geometric environment. So maybe we can also like do a quick quiz. So if you see this figure, do you think A is longer or B is longer?
Yeah, we all vote for A.
Yeah, so I think this is a very simple question for human. But when I tried it like 2 years ago in GPT-4V, actually it tell me the wrong answer. It will say like they are of the same length. And then if I try it this month, even like I think today when I use the model from GPT-5, actually both lines A and B are the model answer like they are of the same length. So it basically means like the model is trying to learn something that is similar to the training data, and they actually recognize this as some visual illusion example that they will always see like if there are two arrows and people ask this comparison between arrows, then most of the cases they are the same length. So, but actually this is a misunderstanding. Like they are just the style similar, but they are not very same example. And then we are thinking like if we can change the image style, maybe the model can answer it differently. So it actually match our assumption that if we change them to the pencils, the model can answer it correctly. Or if we change it to some real image, then the model can also recognize it. So I think based on this example, we actually more assured about we just described earlier. So the model is able to learn about the semantic concepts more about like object concept, relationship concept, or actions. So they can do the alignment, but they are not able to really understand what are the geometrics relationship. For example, this paper from Sanning actually categorized 9 kind of image examples that the model is not able to handle well. So for example, for the first image, if we ask the model where the dog is facing, the model actually cannot answer the orientation correctly. So this part is mainly about the bottleneck about shape and color and pose and orientation. And if we have multiple objects, then we want to figure out their spatial relationship, or for these objects, they should have egocentricness so they could understand the relative spatial relationship. So firstly, this example is like given the cup and table, the model will always say like the cup is on top of the table. But even if the cup is under the table or on the left or on the right side, the model cannot recognize the specific spatial relationship, but just use the prior, saying like whenever they see cup and table, the cup should be on top of the table. And yeah, spatial relationship, even if it's just a very simple relationship, the model actually cannot answer it. And then for this egocentricness, if we just ask the model to describe what is left, what is right, the model actually always make errors. And then if we make the spatial changes in a timeline, then it's kind of like the law of physics. We want to understand the dynamics of the world. And then the state changes actually is a big problem for the current foundation models. If we have the chair in the room, then as human, we can easily imagine the room layout, like the blue chair is behind the red chair, and the yellow chair is behind the blue chair, and the book is on top of the chair that is in front of the blue chair. So in our mind, we will kind of construct this mental model or mental simulation about the environment. But the current foundation model is still always make errors about this kind of example. Like for the example, if we describe the room layout and then we ask the model saying like, if you turn right, what will behind you? So the model actually need to do mental rotation. Then they will sometimes also make errors. And there are a lot of other examples that the model actually has a bottleneck, like transition modeling or spatial reasoning in a large layout, and also navigation and episodic memory. So what we try to do here is we want to see whether the model really has the reasoning ability that can reason about unseen object or unobservable scenario. So for mental models, what we are thinking is more like we get partial observations from the environment. For example, if we have the view from left, right, and the front and behind, then what we can do is we will construct a mental model. This will enable us to imagine the object that is outside of the scene, outside of the picture. So for example, here in the at the viewpoint 4, we can see there's a bag, there's a sofa. But if we ask the question like what is to the left of the black bag, it's actually outside of the image. So what we can do is we need to synthesize the scenario based on these 4 viewpoints that we just see. So we will firstly check about the first viewpoint, like there's a door behind the bag. And then we will check the desk behind the bag in another viewpoint. And then we can understand there's a window, and we can understand there's a sofa. So only if we can like mental rotate this different viewpoint, then we can construct this mental simulation or mental model of the scenario. And if we ask the question like at viewpoint 4, then we will have this mental simulation ability. So if we do the mental simulation, then we can understand like the window is to the left of the bag. So in this example, we actually try to research on what really makes the foundation model bad about reasoning in the space. So we actually collect around 20,000 questions, and then we do a systematic evaluation on these questions, and we identify like for both like rotation type of the question and the amount type of the question and the around type of the question, the model always produce the random based performance. So it's basically like for the different viewpoint construction, the model still have very bad performance. And then we try to teach the model to do this kind of reasoning. So this reasoning, we can do something like we just ask the model to explicitly visualize what is changing between these viewpoints. For example, if we ask the model, like if you are at viewpoint 1 and you move to viewpoint 2, so we can ask the model to do the reasoning step by step. Like between viewpoint 1 and viewpoint 2, we can simulate what happened here. So here we are trying to do the view interpolation. But since the vision generation is very still not very reliable at the current moment, so we just interpolate the ground truth viewpoints. And to our surprise, even if we use the ground truth viewpoint, the model actually still have their performance drop a little bit. It basically means that for the current foundation models, if we provide a lot of visual information, a lot of cases the visual information are the noise rather than the help. So we're thinking like if we cannot directly do the reasoning in the vision space, maybe we just do the reasoning in the language space. We ask the model to generate the reasoning chain step by step. For example, we say like in view 1, I see something, and then in view 2, I see another thing, and then we basically try to reason about like if I change from view 1 to view 2, what is the farthest? So here the reasoning is purely in natural language, and we can see if we ask the model to reason step by step, actually their performance will improve a lot. But the improvement is still like around 10%. And then we try to do something about more structured reasoning. So we are thinking like if we want the model to reasoning about the scenario, it's essentially trying to ask the model to construct a cognitive map. So we try to use the JSON format to represent the cognitive map, including what are the objects in the scenario and what are their position and what are their orientation. So to our surprise, if we actually include this cognitive map-based structure in the reasoning, the model actually has this scaffolding, so their reasoning improve a lot, especially like if we compare to the step-by-step reasoning, the improvement is around 20% improvement. So to summarize, like if we do view interpolation, the model actually cannot improve a lot, but we try to do the natural language reasoning and the cognitive map reasoning. And then if we just do the prompting, their reasoning improvement is still very little. So that's why we're trying to do the SFT-based training earlier. And after SFT-based training, we demonstrate this kind of improvement by 10% improvement and 20% improvement. We are thinking like maybe we can do better of the RL training. So what we try to do here is like we ask the model to sorry. We ask the model to, yeah. Yeah, so this animation is basically show like we try to firstly do the training of the SFT based training, and then we try to open up the model's result to see what actually makes this SFT training better. So here we try to ask the model to generate the cognitive map and then annotate the cognitive map to compare like whether the cognitive map generation is correct. We firstly identify like all the cognitive map format is accurate. So the model always can generate this kind of JSON format. And then we calculate the isomorphic rate, and then we actually realize this isomorphic rate is around only 20%. So that basically means that for the cognitive map construction, if we do the training from maybe the annotated cognitive maps, then we can actually improve the cognitive map construction rate. So we can see the second figure, the vertical axis means isomorphic rate. So we can see it increase from around 10% to around 60%. That basically means like the model's reasoning training is trying to make the model produce better or more accurate cognitive maps. So the improved free-form reasoning actually means like there is better cognitive maps. And then we are trying to get the model have better improvement, especially in this spatial reasoning task. So we try to add the reinforcement learning as another stage after the self-supervised fine-tuning. So this stage is just we ask the model to reason about this spatial reasoning question, and if it's correct, we give some positive reward, and if it's wrong, then we give the negative reward. So we can see now we can boost the performance around 30%. So that's another huge boost. And basically what we are trying to do here is we try to ask the model to reason about the space, especially about the unseen object. And this kind of reasoning will force the model to imagine what these objects are, how these objects are connected, and what are their cognitive maps. And then we try to also do the training. So for the training part, we identify like the training is highly rely on these structures, especially we represent them as the JSON-based kind of semi-symbolic structure, then the model actually can understand better about this cognitive map. So that is the first line of work we're doing, trying to do the state estimation. And then the second line of work we're doing is mainly trying to teach the model reason about the action. So that is trying to learn about the Markov decision process policy. For this policy learning, if we try to predict the action, we firstly try to ask the model to just maybe use the large language model as the MDP proxy and then predict the action. And this is our region framework, trying to train the agents by reinforcing reasoning. The difference between the previous reinforcement learning work is that we only see the success in the like a verifiable reward environment earlier. Like if we have the mathematical reasoning task, we ask the large language model to generate the answer to mathematical questions, and then we can get the reward about whether this is correct or this is wrong. And this is what we mean by we are using the verifiable reward, and we achieve great success with reinforcement learning. But if we change it to the agent environment, where we don't just have a single turn-based question, but we actually have a multi-turn interaction, and we don't have the finite problem anymore. We actually have infinite state combinations. And another thing is we are not just rely on one answer, but if we want to achieve the goal, there can be alternative paths to achieve the goal. And also, we are not just observe the entire state by just checking the questions, but in the environment, it's kind of partially observable environment, like the agent or the large foundation model can only see part of the environment state, so that's the observation. And then we basically try to handle these difficulties. The first thing we try to handle is the multi-turn interaction. That the model is not getting the feedback at each turn, but just getting the feedback after a long sequence of actions to decide whether this sequence of actions will be achieving the goal. And then for the state-wise, we are not just observe the entire state accurately. We can only do the partial observation. So sometimes the state estimation is also wrong. As a result, if we put them into a Markov decision process, then what we are learning is here we have the state action sequence. And then after each action, we try to collect the reward. So if we try to ask the foundation model learn from this sequence directly, one thing we can do is we can ask the model to firstly do the rollout and then do the update. So essentially, what we try to do here is we try to extend the single turn rollout to multi-turn rollout. So for the multi-turn rollout part, we firstly ask the large language model to interact with the environment, so we can get the state action sequence, and then we update this large language model. So if we just summarize what we talk about to learn from this action sequence, we try to change from optimize a single turn action to optimize the multi-turn trajectory. And then we try to use the traditional PPO algorithm to do the optimization. So the optimization goal is trying to make the full trajectory to have this cumulative reward, and then just make this cumulative reward to be fit in the framework of PPO. In detail, when we are trying to roll out the trajectory, we try to firstly ask the model to generate the output of the action, and this output is based on the current state. So here, the trajectory is about like if I am seeing this current state, what should be the action in the next step. And the model firstly will generate some thinking tokens, and then this action will be executed in this environment so we can get the feedback. That feedback contains the next state, like after we execute this action, what happened, and also contain some reward from the environment. But we are not quite sure about like when the model will finish the rollout. So we actually ask the model to decide by themselves, like until they feel it's actually achieving the goal, then we actually ask the model to terminate the rollout so we can get the trajectory, and then we can get the trajectory level reward so we can accumulate the reward here. And after that, after we get the trajectory, we use this trajectory to update the large language model using PPO algorithm. With what we are doing here is more about like if I have like one initial state and one goal state. There can be multiple trajectories to achieve this goal state. So we actually normalize these trajectories all together. So that will be the reward normalization. And then we firstly just use this simple implementation to the agent task like vending machine, Sokoban, frozen lake, and web shop. We actually identify that for the current foundation model, if they try to play this very simple game like Sokoban or frozen lake, their performance is super bad. They basically just get like 10% accuracy. And then if we ask the model to just directly do the PPO-based reinforcement learning training as we just described, like roll out the state action sequences, then the model actually cannot get a stable training. So what happened is, like the blue lines here, that the model will always firstly get their success rate up a little bit, and then directly drop to around 0. So it's kind of collapse behavior that the model is not really learning something, but they collapse after several rounds. So the first thing we are trying to do is to understand this collapse, like why it will happen that the model will directly drop the success rate to 0. And then if we check these steps that the model dropped to 0, like the step 150, we can see like the reasoning chain will be always the same. So even if I train like multiple steps, the models actually just converge to the same reasoning chain. Like my initial intention is to pick armed dragon, and my first action is to go for armed dragon. So that is something very unfortunate, and we think it's more like a local minimum. So the model is not really trying to do the reasoning anymore. They're just trying to repeat the same reasoning chain all the time. So we call that echo trap, because the echo part means like the model is repeating their reasoning chain. And for this echo trap, we try to indicate some indicator like the reward variance and gradient norm spec, and also the entropy. Use them and monitor them to understand like when the collapse will happen. And then we try to avoid the collapse, like avoid the model to stuck in the local minimum and always repeat their reasoning chain. So we identify that if we want the model to have this diversity, then we basically ask the model to get the reward that is very diverse. So the reward should have high variance, like change from the left to the right part. And then the simple way to do it is just we try to ask the model to only keep the trajectory that have the high reward variance. And we can just rank all the trajectory rollouts, and then we can keep the top 5% trajectories that the ranked by the variance. And then we can also keep the 50% of the trajectory of high variance, or the 75% of the trajectories. And we can see that compared to we just leverage all the trajectories, the model actually can get much better result if we do the filtering. So it's kind of like we are not using all the data to train the model. We just use the high quality data that is diverse, that is actually accurate to help the model learn. And then this kind of stabilize the training. Basically, to summarize, we have this filter by high reward variance part, and then we can also leverage the training tricks from other single turn RL algorithm. Like we can have the different clipping, and we can remove the KL constraint. So the model can finally get a stable reinforcement learning training. And then we can see the orange line is much better than the blue line here. So in this framework, what we try to do here is we try to learn about how we can do the rollout in a more structured way. We ask the model to get this state action sequence first, and then we can ask the model to learn from the reward based on this state action sequence in the multi-turn environment, especially for the trajectory part, we ask the model to have all the high variance reward by filtering out some trajectories, and then the model can finally get the stable training. And the code part is very easy to use, so we actually have around 2,000 GitHub stars for this work already. And we just talk about how we can teach the model to act, to generate the action sequences. And the next thing is we want to combine the first part we talk about the environment to this action sequence. So that is meaning we actually want the model to not only act, but also see the environment. So we can have multimodal agent. Essentially, if we are still working on this Sokoban task, we want the model to input this Sokoban image directly rather than convert the Sokoban image to text. For example, if we try to ask the model to consume the visual state, something we can do is we can ask the model to also reason about this state and then check whether their interpretation for the state is correct or not. And for this interpretation from the models, we can see there are different formats. We can ask the model to verbalize the state in natural language or in the symbolic representation or the structured representation. And if we ask the model to see the environment, this actually means we are not observing the environment directly, but we try to ask the model to firstly check the environment, and then they can get the observation from the environment, and then we can understand what happens. So it's actually partially observable environment. And if we recall like what we are learning from the MDP process, we basically try to learn the state changes. We have the current state, we have the action, and then we try to predict the next state. But for the POM-DP, the partially observable MDP process, we will firstly have observation. So the observation will be perceived to be the state, and the state will be transitioned after the action being executed. So the difference between MDP and POM-DP is the introduction of the observation. And then this part, we actually call it word model because it's trying to describe what will happen after this action and how the word will be changed after the action is executed. So this part, we can see there are two things. The first thing is we want the model to do the state estimation, like given the observation, we want to have the state. And what we can implement here is like in the algorithm, we ask the VLM agents to firstly generate the observation tokens. So they can verbalize the current state, and then we ask the model to serve as a judge to compare the predicted state and the ground truth state. So the model actually can get some reward about whether the observation is correct or not. And the next part of the word model is the transition modeling part. So we have the action and we ask the model to predict what will happen in the next state after the action is executed. So here, in the implementation part, we try to introduce the prediction tokens, and we ask the model to predict next state, and then predict the compare with the next state ground truth. So we can see like with this kind of reward shaping, the model actually can do the step-by-step thinking to verbalize like where the agent is and how they can achieve the final goal. And this is a successful example that the model is able to think and answer the question. And we also see like we have a more complicated scenario, like we can ask the model to reason about navigation and reason about robot manipulation. And then, so this is the part that we're actually working on about asking the model to not only just act, but also see and act, so we can have this region vision framework. Yeah, I'm not sure whether there's any questions.
Okay, so first of all, let's thank our speaker. Thank you for the presentation. Any other questions from online or in audience? Any other questions? For online people, you can just raise your hand and
Hello.
Yeah, please, Yuni.
Yeah, hello. Thanks for the presentation. It's really, really interesting and really great. I wonder, like, because I'm also working in reinforcement learning, so I heard about the high variance reward thing, and I wonder, like, how can you? Because we all know, like, a stable reward environment is quite important. So when you use like high variance reward, how can you like secure or make sure the like reward environment is stable?
Yeah, so when we are trying to generate these trajectories, we actually ask the model to roll out a lot of trajectories, and then we can just like rank all the trajectories to select the trajectory that is diverse. And also during this selection, we can actually just select the reward that when we have the trajectory that is long, that is like matching our kind of observation that the trajectory when the trajectory is long, a lot of cases the model will think more, and then the training performance will be better. So I think when we rank the trajectories, we try to get the reward that is diverse but still high quality. And then if we just only keep this 25% of the trajectory, actually their performance will be much better. So I think that is how we can control the training to be more stable. So for the stable of the reward, is this something you want to ask?
Yeah, Kenna, thanks for your answer. So I think it's like when you say you filter out 25% of the trajectory, like especially when you have a long trajectory, so it's hard to design the reward. But that's why I have the question about the stable reward environment.
Uh-huh.
Anyway, like thanks
Yeah,
for
yeah.
your answer. Yeah, I think
Yeah,
I kind of get it.
Yeah, another thing is like when we are working on this reward collection, so we actually, as you mentioned, like sometimes the reward is not, I think a lot of cases is very sparse, and sometimes
Yeah.
the model training is not stable. So in this kind of work, when we are trying to ask the model to serve as a judge to compare the current state with the ground truth current state and the next state with ground truth next state, this is another way we try to make the reward to be stable. So we just ask the model to have a kind of denser reward. And then another thing here is if we use LM as a judge, so I think their performance, a lot of cases, we also need some controlling. So which LM we are selecting can be served as a proxy to produce the reward. We actually also try different models, and then we also learn about like if we really want to understand the like spatial representation of the state, we actually need to briefly fine-tune the judge part. So even if we just use the LM as a judge, we do some fine-tuning to make this part of the reward more stable as well.
Okay, thank you for the insight.
Feng, you can unmute yourself.
Yep. Thank you, Manling. It's a great talk, and I'm Feng from Edinburgh as well. So I actually have two questions. One is specific about the LLM as a judge. So because you are basically comparing, you have a ground truth state and you have a state generated by an agent, right? So what is the motivation of using LLM as a judge without, doing some kind of metric-based computation?
Yeah, so here, the current state and next state, they are represent using different formats. So we talk about like here, when we have the verbalization, we can have different format of the verbalization. We can have natural language, we can have symbolic, we can have structured. So the comparison between the ground truth representation will also depend on like what kind of verbalization the model choose to use. So here, like if it's the natural language based output from the model, we actually compare with the natural language verbalization from the state. I mean the ground truth part, we actually need to directly use the ground truth from the environment that the agent is located in, like 0, 0, this kind of position, and where is the box. So I think here, the comparison sometimes will have this problem, like we cannot do token by token comparison because the ground truth state and the verbalization from the model, they may be not in the same format, or maybe they just have different natural language style. So if we use the large language model as a judge, we can do the comparison between the so this part, I think the comparison between the predicted state and the ground truth state. So they can be any format produced by the model, and the ground truth can always just be the kind of position or other metadata we observe from the environment. So the comparison can be more accurate. We also try other algorithm, like I think we try to do something like encode this prediction and the ground truth into embeddings and compare the embeddings. They are not really working well, so we just use LLM as judge.
But does it make any mistakes from your experience? Is there any risk that the judge make mistakes?
Yeah, so that's also related to the last question, that how we can make the reward more stable. So we try to we actually also observe something very interesting. Like if we are trying to do the robot manipulation, we can see here the observation representation is JSON format, but it's very I think structured kind of, and then if we compare this kind of observation to the ground truth observation, the current foundation model sometimes will make errors about comparing the numbers. So I do feel for the numerical reasoning, the current foundation model is still lagging behind. So for this part, if the model is making errors, we basically recognize like we need to train the model slightly or fine-tune the model slightly about recognizing this format, like this JSON format about we have the object and we have the object coordinates. So they need to understand this. And the fine-tuning part, we can just treat it as a cold start process, like a warm-up. So the fine-tuning dataset, they are not the training sequences. They are just like this environment kind of format-based fine-tuning. So that is how we can maybe fine-tune this LM as a judge part to make sure it can understand all the current state and the next state. But I think this part it's very reliable if you are handling some natural language task. For example, if you are doing like web shopping or this other computer use agent, then you don't need the fine-tuning. But if you are working on robotics and you want the model to serve as a judge for the like JSON-based coordinate state, maybe some fine-tuning will be much more helpful.
Yeah, great. Thank you. And so there is a second question, more general, because you do a lot of work about spatial reasoning of VLMs, and I can see that when you apply some of your proposed methods, you have a increased accuracy, like from, for example, 38% to 60%, something like that, right? So the question is about, do you observe any patterns that after your proposed method it still fails? Like what kind of thing is still fail? For example, recognizing the perspective of camera. And do you think at the current stage, the VLM's spatial reasoning ability can already be applied to applications like robotics, this kind of thing?
Yeah, so that's a great question. We also recognize like there are some problem, and I think one thing maybe I can quickly also show some example very quickly. It's some work we try to submit to Clear, and yeah. Sorry. So something we're working on. For example, like if we are asking the model to predict the sequences, the observation sequences given the action. Maybe the last is better. So for example, for robotics, what we are doing is like for each state, we have the scene graph, and then we have the action, and ask the model to execute the action to transition to the next scene graph, and then it's kind of a scene graph action sequences. But this scene graph part is a kind of like observation. We just observe what is in the scenario, and then what we can do here is we actually have two types of the task. One is the forward word modeling, and another one is the inverse word modeling. So we can get the model actually just firstly try to, given the observation and action, to predict a sequence of the observation, or given the observation and observation changes, and trying to predict the sequence of the action that make these changes. So these are two different tasks we are identifying. The current foundation model always have problem. So I think the accuracy is very low, especially if we ask the model to do the planning, so predict a sequence of the actions. They actually can only get around like 50 based accuracy, 50% based accuracy. And then yeah, we also identify some very interesting features, like factors, what actually make this prediction very bad, and what actually is now related to this prediction. So I think for this kind of task, if we are really trying to do robot manipulation, how we can ask the model to understand the word model part, not just the trying to understand like what are the object and how the object look like, and like their shape, their color. So the questions really about actions and the state changes, especially these subtle state changes, is very hard for the current model.
Yeah, that's great. That's great. Thank you for the sharing. Yeah, I have no more questions. Thank you.
Thank you.
Okay, I think the last question is from chat, Xuelong. I think it's related to how the cognitive map generated, and how can we ensure they are correct and free from hallucination, thus they are clean data for SFT.
Yeah, so yeah, I can also share the screen. So I think for the data generated, we actually ask the model to have this kind of evaluation. So we have this kind of metrics that we can evaluate whether the model is following the correct format, and then whether the graph is really generated correctly. So for the ground truth part, the data annotation, we actually annotate, I think, 10,000 data for that. The annotation is mainly about like when we are trying to collect the data like this. So we ask the human to annotate what are the objects in the environment, and then they will actually annotate their spatial relationships. So that is how we kind of create these questions, like we have the objects, and then we can ask about different spatial relationship between the object pairs. So when we do the annotation, we firstly ask annotators to annotate the entire object set and their spatial relationship. And this annotation later was used as the cognitive map annotation. So that is how we have the cognitive map annotation, this part. And then the annotation will be used as I think fine-tuning part. So that is what you mentioned about how we can train the model to make them have like less hallucination. So I think one thing we observe is like when we show this figure, like the model is trying to follow the format but has the wrong content. So for example, the valid cognitive map rate basically means the model is following the format, but the overall similarity and the isomorphic rate is very low, means like the numbers within the map is actually wrong. So that is the hallucination part. If we do not do the training, the hallucination is very, I think still has this very bad result that most numbers, like if we see 20%, like more than 20% of the numbers are actually hallucinated or just the wrong numbers. And if we train the model, we can see when we train the model on reasoning task, their cognitive map actually also improve. So this is I think the intuition that when the model is trying to learn the reasoning, they're actually trying to figure out the cognitive map, and it can be improved from like less than 20% accuracy to around 50% accuracy.
Yeah, that's how I feel when I first saw the figure. It's looking like they're really good at matching the format, but somehow within the content, the language model somehow just misleading themselves.
Mm-hmm.
Yeah. Okay, I think we are about time. So as a reminder, this is a monthly seminar. If you guys are interested, welcome to subscribe to our newsletter. And I think that's it today. Thank you, Manling. Thanks to our speaker again. And I hope you guys have a nice day.
Thank you. Really appreciate the opportunity. Thank you.
All right. Thank you. All
Thank
right.
you.